All right, so today we're going to be talking about pixel-to-pixel translation. What are these transpose convolution things that we're using in Lab 4? And yeah, that's what we're going to be looking at today. To start off with, we have a couple of announcements. Labs 3 and 4 are due Saturday, as well as readings for this week. Any questions on any of those? Okay. Also, this isn't on the slide, but there are 2 jobs that I wanted to advertise. So my research advisor, Dr. David Wingate in the computer science department, is looking for someone to develop infrastructure for data science, for training neural networks on the data science cluster in the computer science department. And then also looking for some help developing language models, which we have not yet looked at, but basically there are certain architecture of neural network that's trained on text. So that's one of them. If you're interested, let me know. And then another is I'm looking for a research assistant to work with me on deep learning and with chemistry applications. Chemistry background is not required, though it's helpful. So yeah, if you're interested in either of those opportunities, let me know and we can talk some more. So last time we talked about activation functions and initialization strategies, and we saw how those 2 things kind of play together, where we looked at activation functions from sigmoid to ReLU, and we talked about initialization strategies like Xavier, key, orthogonal initialization. And we saw that for ReLU networks, Xavier initialization resulted in dying gradients, but with a small correction and using key initialization, ReLU networks did pretty well. So today we are going to be talking about specific training tasks, pixel-to-pixel translation, and then we'll be talking about transpose convolutions, and then the deep UNet architecture, which you all get to implement from scratch in Lab 4. So first off, just a look at a couple of different variations on convolutional neural networks. This is called the inception network architecture, which got the catchy name of GoogleNet. You can guess where the creators of it came from. So basically, the idea is that we have filters of different sizes, and they are applied to the previous layer and then concatenated in the output. And I'm actually noticing something right now. I think there's something a bit misleading about this visualization. Any thoughts on what that might be? I don't know really anything about this network architecture other than this slide, but there's something that seems kind of weird to me about how this looks relative to the inputs. Yeah, what do you think? Looks like there's some reshaping being done. What do you mean by that? Okay, so you're pointing out that we have different filter sizes and they're all getting the same spatial dimension in the output. I don't think that's a problem actually, because if you think about it, each filter, if we have the proper padding, should produce an output of the same size as the input. And so I guess if there's no padding, then you're right, they should have different spatial dimensions, but usually we kind of assume padding. And so I'm actually fine with the spatial dimensions of that output. Yeah, what do you think? Yeah. That's what I was thinking, yeah. So that's exactly right. So he's pointing out that these filters, the fact that there are different sizes in this output makes it seem like the output size depends on the the filter dimensions, which is not the case. Yeah, so each filter should produce one equal sized slice of this output matrix, of this output tensor. So that's kind of interesting the way they visualize that. If you're interested, go read the paper and see if they have a good reason for the way that they drew that. But yeah, if you just have 4 equally sized filters, they should each produce a filter map or even 4 different size filters. Each of them should produce an activation map of the same spatial dimensions and the same channel dimensions, which is 1. And then, yeah, they should just be 7. Okay. So as a kind of review on convolutional neural networks, the idea is we find basic features like textures using a small filter. Then we zoom out and find larger and more complex filters by stacking more and more of those filters. And then continue, etc., until we're recognizing larger objects like dog ears, dog faces, etc. And then one important note is that usually in the end, we apply a fully connected network to translate that last feature vector into a certain scores for different classes. So this is one such convolutional architecture, and let's see how this works. So we start with dimensions 24 by 24 by 3. What does the 3 represent? Panels, RGB. Then we apply convolutional layer, and we get an output activation map of size 224 by 224 by 64. So quick question, if we are using a 3 by 3 filter and we're getting an output and let's say stride 1, how much padding do we have if we're starting with 224 and we're getting 224? With a 3 by 3 filter. Yeah. Yeah, padding of 1, exactly. And what if we had a 5 by 5 filter? How much padding would there be? 2, 7 by 7, 3. Yeah, good. And then how many of those filters are there in that first layer? 64. Great. You guys got this. All right. And yeah, just a reminder, the reason why we had 64 of those is because each one of those 3 by 3 by 3 filters produces one of these channels. So if you get 64 channels, we would have 64 filters. And you can see it looks like we go from 224 to 112. Any guesses what they might have done with their convolutions here? Added a stride of 2. That's one possibility. In this case, they actually used a max pooling layer, which we mentioned last time, but a max pooling takes all pixels in a 4 by 4 square and returns the maximum pixel in that square. And so max pooling is one strategy for reducing dimension, but also increasing the stride of your convolutions to have that same effect. You see we gradually shrink the spatial dimensions and increase the channel dimensions until we end up with a 7 by 7 by 512 activation map, at which point we go to a 1 by 1 by 4096 activation map. Any ideas how we might go from 7 by 7 by 512 to 1 by 1 by 4096? What type of convolutional layer? What filter size? What stride? What kind of padding? Let's try to hear from someone we haven't heard from in a while. How would we get from 7 by 7 by 512 to 1 by 1 by 4096? Yeah. Yeah, exactly. A 7 by 7 kernel. How much padding? Zero padding. And yeah, I guess it would actually be a 7 by 7 by 512 kernel. And then 4096 of those would get us to 1 by 1 by 4096. Yep, and then we apply a fully connected layer to get that into a 1 by 1 by 1000 output vector. And so what would be the dimensions of that fully connected layer? I always have to think which is the height and which is the width. How would we go from 4096 to 1000? What would be the dimensions of W? 4096 by 1000. It's actually the opposite. So it would be 1000 by 4096 because our input vector is 4096, and then our output vector is 1000. But yeah, that is correct. Then we get apply a softmax, and we get scores. So that's how you create a convolutional classifier. All right. Yeah, Travis.
Structure of like that for like
Yeah, it's a good question. So Travis is asking why we're trying to shrink the spatial dimension down to 1. And I think my intuition for it is that we are trying to reduce any kind of spatial information. We're trying to capture all spatial information before we go into a fully connected layer. Because a fully connected layer doesn't have any kind of bias about spatial information. And so basically, and it's what it says here. So we're applying convolutions and zooming out, and basically we're going from spatial information into higher or more abstract representations, like has an eye, or has a nose, or has an ear. And so we end up with 4096 features that are independent of spatial relationship, that have where we no longer have a dimension that represents spatial relationship. And then we find the best connection. What that last fully connected layer does is it finds basically the weighted combination of those features that maps to each of those 1000 classes. So I guess to sum that up, is the point of shrinking the spatial dimension is so that we never apply a fully connected layer to something that still has spatial significance. So you could think of it as zooming out. That's definitely one way to think of it. Although you'll get that kind of zooming out effect as you go deeper in the network, anyways. So, like in theory, I think you could still have you could maintain the spatial dimension up to that last layer. It would just be more computationally expensive, but yeah, I guess it's up to you how you want to think about it in your head. But I think what I'm trying to say is that zooming out kind of happens by virtue of having a deep neural network, even if you aren't shrinking the spatial dimension. Okay, so this is how you make that VGG architecture. Com2D, and then this is using the Keras deep learning framework, not PyTorch. So PyTorch syntax will look a little different. Keras allows you to include your activation in each layer. But yeah, com2D, maxpool, com2D, maxpool, etc. And that's pretty similar to what your code will look like for the UNet. Okay, so let's talk about memory for a little bit. So let's try to figure out what everything in this diagram says. So here we have the names of each of the layers. The number following the layer indicates the number of input channels to that layer. And then this tensor size represents the size of the activations at that layer. So the total memory usage at each layer of the network will be the size of the activation vector, which is this tensor size, plus the size of the weights used to compute those activations. So in this case, that is 224 times 224 times 16 from the activations at that first layer, plus 3 times 3 times 3 times 64 numbers in our weights. Can someone explain to me where each of the numbers came in this weight calculation? Yeah, Jacob. Yeah, 3 by 3 by 3 is the kernel size. So actually 64 in this case is the number of filters. And so this is the number of filters that results in an output of size, panel size 64. Does that make sense? So the input had size 3, and you'll see the last number in the tensor size of the previous layer becomes the last number in the kernel size of the next layer. So 3, 3, 64, 64, 64, 64, 128, 128, etc. So you can see that the most memory and compute time is used in the earliest layers. And this is because our activation map is still so big. And that's another justification, Travis, for shrinking that spatial dimension, is because as we shrink this, the activation size, our memory usage becomes really low. You can see it starts at about 3.2 million and gets down to about 25,000. Yeah, so then we get through all of our convolutional layers, and it looks like hard to see. It's hard to compare the memory required for our activations versus our weights, but I think in general the activations are going to be a lot larger for a convolutional network until we get to the fully connected layer. Look at that. We have the size of our activations is only 4096. Oh, and actually, I misled you. Sorry, this memory is not the sum of the tensor size and the weights. This memory is just the memory corresponding to the activations. So at the beginning, the activations take up 3.2 megabytes of memory compared to only 1.7 kilobytes for the weights. And by the end, yeah, we have much less memory for activations. But then we get to the fully connected layer where our activations are only about 4 kilobytes of memory. And then what do we have to do? You told us that we needed a 4096 7 by 7 by 512 convolutional layers. Well, that results in 103 megabytes of memory of storage. So hopefully that kind of gives you an idea of like the order of magnitude of that we're looking at when it comes to storing activations versus storing weights. In a purely convolutional neural network, you're going to have, in general, the activations will be much more memory intensive than the weights. But anytime you introduce a fully connected layer, your neural network parameters are going to spike significantly. So yeah, that brings us to a total memory for our forward pass is 89 megabytes to store the forward activations and 134 megabytes to store our neural network weights. Does anyone remember why we need to hang on to our forward activations? Remember, thinking back to our automatic differentiation and back propagation, why do we need to hold on to the forward pass? Yeah. Exactly. We need the forward pass at outputs at each step in order to compute the backwards gradient at that step. And so there are actually ways to do this. Basically, where you run a forward pass at each step of the back propagation. You can imagine how computationally expensive that is. So in general, yeah, we just store our entire forward pass, and then I think this might be wrong actually. So can anyone, so it's saying that we need this slide says that we need 89 megabytes for backprop, but I think that's incorrect. Can any of you see if you agree with me? Do you agree with me or disagree that we should have 89 megabytes for backprop? And I'll just kind of just zooming out for context. There's a reason why we're focusing so much on this nitty-gritty memory management stuff. It's because you are using Google Colab to train these neural networks, and you are going to run into memory issues. You're going to run into memory limits. And so it's really important to understand where our memory bottlenecks are. So yeah, just by raise of hands, who thinks that we should have 89 megabytes of storage for our backward pass? Okay, raise your hand if you think it should be something else. All right, and it appears that about 90% of this class is some third other thing. All right, so the people who raised their hand to say that they thought it might be something else, what, just throw something out there. Why do you think it might be something else? Yeah. You need to add the weights. What? Yeah, explain what you mean. Mm-hmm. Yeah, so we definitely need the weights. So we're definitely going to need 134 plus 89. But then we're wondering if we need that, we always need our weights, whether it's forward pass or backward pass. Are you saying another copy of this for the backprop, or? Okay, you're not saying that. Okay. Yeah, what do you think? Yeah, so you said that the activations and weights are already stored, so you wouldn't need to store anything in addition to those. I'm not sure I agree with you. We'll hear one more, and then I'll tell you what I think, and you can tell me if you agree. Dane,
it bothers me that we are not talking about the biases.
Oh, it bothers you that we're not talking about the biases. It doesn't bother me because biases are like nothing in memory. It's okay. I'm just giving you a hard time. Yeah, no, it's fair. We are not accounting for biases in these layers. So that is a good thing to point out. But in practice, bias tends to be negligible. Yeah, Brendan?
Do we have to store all 22 megabytes of memory going forward?
All 22 million parameters. So that's kind of what I mentioned. We don't necessarily have to, but it means that we have to recompute that forward pass basically at each layer that we go backwards. So I'm going to tell you what I think. I think that on the backward pass, we should, instead of having plus 89 megabytes, we should have plus 134 megabytes, because or is that, I'm not sure if this is number of parameters or megabytes. It might just be parameters. But the point is, I think we should need to have double the memory for for the parameters because we need to store the gradient when we compute that. And so I think this should be plus 134 times 4 bytes per parameter. So yeah, like about 500 megabytes per backdrop to store our the values of our gradients. Now you'll also see this. It says if using backdrop optimization, and we're gonna talk about this next lecture, Atom, Adigrad, and or RMS drop. These are alternatives to gradient descent. If we're using any of these, we need to multiply this number by 3 for to cache certain information about our gradients. So basically, just as a short preview, there are some optimizers that basically keep track of the trajectory of our gradients. They're called momentum-based optimizers. And they store what are called the first and or the second moment of your gradient. So that basically allows your gradient, instead of zigzagging back and forth, to basically move like a rolling ball down a hill. And to do that, you store the first and second moments of your gradients, which again these would be multipliers on the parameters. And so I think what this should be 89 megabytes for the forward pass, 134 times 4, so we'll say 500 megabytes for the weights, 500 megabytes for the gradients, and then maybe possibly 500 more or 1,000 more if you're using some other optimization algorithm. Any questions on that? That was a lot. Yeah, Dane.
Do you need to keep in memory all of your gradients, or can you work with a piece and just use a small amount?
Do you need to keep all of your gradients in memory? So I mean, one thing that, I don't know if this is what you're getting at, but once you compute the gradient, you could apply that weight update immediately. And then, however, you still need that gradient in order to compute the next gradient using the chain rule of derivatives. But once you've computed that next gradient, you can discard that original gradient. If that's what you're saying. I'm pretty sure that you can do that. Yeah. In practice, PyTorch does not do that. They just store all of your gradients in memory. And I think PyTorch, yeah, this is also a good point to make. PyTorch is made to be easily interpretable and to make it really easy to see what's happening at each step of training. PyTorch is probably the slowest deep learning framework. So like TensorFlow and I think MXNet and JAX, and they use a compiled neural network. And I would guess that they use tricks like the one you just described for gradient updates so that you don't have to store all of those gradients. Okay, so then there's also this thing called transfer learning, which very possibly could come into play for your final projects. So if you have a big data set, it's no problem to train an entire deep neural network with many parameters. But for a small data set, it can be very easy for your neural network to overfit, or basically to memorize your training data and not generalize to any new data. So a common trick that people use is called transfer learning. You start with a neural network trained on a large data set, and then you use those trained weights as a starting point for training on your small data set. And so there's a data set called ImageNet, which contains something like 100 or 200 million, I'm not sure, a lot of images. And there are image recognition networks that have been trained on that huge data set. And so if you want to train your network on fine-grained classification of different species of bird, your data set is probably going to be smaller than that data set. And so you might start with a network trained on ImageNet and then fine-tune it on your bird species data set. And this slide says to freeze weights during fine tuning, but I'm pretty sure that actually that you can just let your neural network train end to end. And it usually does better than freezing weights during fine tuning. So yeah, and what I mean by freezing weights is during gradient updates, you only update the last layer of the neural network. So basically none of the learned features change, you just learn a different weighted combination of those features. So that's an option. Yeah.
So this is basically a way of like, you can have kind of like roughly what you want, and then kind of find, but like,
Exactly.
this gets most of the way there.
Exactly. Yep. Yeah. Exactly same network. Exactly. Yeah, for our new tests. Yeah, we learn, kind of like I said, we start with this super good feature extractor is basically what this trunk of the network is. And then we learn a different weighted combination of those features for our new classification test. Okay, so your lab this week is cancer detection. The goal is to take an input image and label each pixel as cancerous or not cancerous. So we take, to do that, instead of taking as input an image and producing a vector of length 10 or length 1000 corresponding to your different classes, you will do the same thing, except you will produce that vector for every pixel of your output image. You'll classify each pixel of the output image. So let's go through a kind of quick overview of this problem. So there are lots of pixel-to-pixel problems. Here are a couple. Perhaps we want to go from labels of a street to generate a realistic image of a street. That is one possible input to output. You could also imagine reversing that problem where instead of generating a picture of a street, you want to start with a picture of a street and label every pixel in that street as belonging to the road, a car, a pedestrian, etc. Another one, here we have a satellite image of terrain, and you want to predict a Google Maps rendition of that terrain. That could be another pixel-to-pixel task. Here we have, I think this is mapping daytime to nighttime. So take an image taken at daytime and project it to nighttime. Here we have labels, it looks like, of windows and a facade, and we want to translate that to an image. Here we have, we're rendering an image from black and white to color. And again, all of these pixel-to-pixel tasks, you can imagine reversing as well. So these are some example results of a network trained to do aerial photo to map, and then the reverse problem. And for my completely uneducated, well, I kind of know what a Google Maps should look like. I'm not really sure what a satellite image should look like, but it seems like both of them are doing pretty well. Okay, so then these are some example results of doing label to image rendering. And yeah, you can see a lot of the time it gets pretty close. Can you see any problems with going one direction versus the other in this pixel-to-pixel labeling scenario? Spencer. Totally, yeah. So Spencer said that, yeah, in one direction of this problem, it's pretty easy to see that there's probably only one correct label for this image of bikers and pedestrians. However, you can imagine in going in the opposite direction, there are probably many photos that could satisfy this kind of pixel by pixel labeling. And so there's, I think, something about this, this kind of input, like minimalist input to dense output, this problem, it seems a little ill-posed to me. And later in this class, we will learn about generative models, where instead of producing a single image as output, they produce a distribution of images as the output, which I think is a better way to approach this label to image problem. That's just a little bit of a preview. Okay, so again, rendering video from a label of the image. And rendering facades, going from day to night. And yeah, some of them it does better than others. Rendering handbags. Kind of amazed how well it did on this one. Kind of impressive. Rendering shoes. So you can start to kind of imagine some of the commercial applications of this. And people are doing this. They are using deep learning to design new products based on sketches or drawings. Okay, so the UNet architecture takes as input a 572 by 572 by 1 image and produces an output segmentation map of size 388 by 388 by 2. The way it does this is it applies convolutions that preserve the spatial dimensions, max pool layers to shrink spatial dimensions, and then the kind of secret sauce of this UNet architecture is that we have these gray arrows going across. Any idea what those gray arrows might be? Try to hear from someone we haven't heard from yet. Yeah. Exactly. Yeah. So we have some forking paths here. So what you said is exactly right. So you see this dashed line cropped from this image is then copied across to and is concatenated with the output coming from the other fork of the network. And it's concatenated along the channel dimension, and then you just apply convolutions from there on out. So does anyone have any idea of why those, we'll call them skip connections, why do you think those skip connections might be helpful? Based on what you know about what networks learn at the early and late stages. Yeah. That's a great point. So saving on memory. So yeah, you're providing basically pixel by pixel granular information at the late stages of the network without using the memory to preserve that spatial, those large spatial dimensions as you go, as you increase the number of channels in the network. Yeah, great point. Yeah, what do you think? I think that's a brilliant explanation. I think that's a great idea of what could be happening here. So I'll just repeat that. So you said basically in the case of cancer, we're going from each pixel or each region of cancer being represented by, say, 7 by 7 pixels, being represented by only 1 pixel here at these bottom layers where we're only 32 by 32. And we want some way to be able to kind of outline that region at the last layers of the neural network. And so we're going to make it easier for our neural network and pass those early features all the way across. I think that's a great idea. And yeah, some more intuition for what's happening here is as far as like lower level coarse features versus higher level abstract features, where do we tend to learn the coarse features? At the beginning or the end of the convolutional network? Yeah, we tend to learn coarse features at the beginning and abstract features at the end. And so you can imagine that what's happening here is these lower level coarse features we're allowing them to mix with higher level, more abstract features. And hopefully that's more helpful than having only abstract or only coarse features. Yeah. Great question. Do you have to do anything special when training this? So your computation graph is going to look a lot more complicated, right? Because now you have multiple inputs. And so the short answer is yes, you can still use backprop. But the computation graph is more complicated. Yeah. You backpropagate through the skip connections. Yeah. And we actually didn't look at this when we were doing the chain rule of derivatives, but when you have multiple inputs, the chain rule tells you that the derivative is the sum of the derivatives from each path. Yeah. Jared. Yeah, so when I say by abstract, I mean, oh man, I'm trying to remember the artist. Abstract basically means zoomed out, or in the sense that I'm using it, where basically you are learning features that are very high on the hierarchy of features, where coarse grain is like wrinkles, and abstract is a concept that's composed of many other concepts built together. Okay, yeah.
Analogous to the neural net,
Good question. Yeah, so the question is whether there's such thing, if we take this idea of skip connections to the limit, is there such thing as basically connecting all of these in a spiderweb spaghetti thing of connections? And the answer is yes. It's called dense net. And actually, this is another really interesting property of these skip connections. I think this thing corresponds to dense net, the architecture with connections everywhere. So what we're looking at are the loss surfaces. So this is the loss, and then these are on the two x and y axes are two randomly selected weights. So yeah, what do you notice about these architectures with and without skip connections? Yeah.
seems like the first one can connect fast.
Yeah, exactly. So this first landscape is obviously very bumpy, and we have a bunch of local minima that you can imagine an optimizer getting stuck in versus this one on the right. As long as you have a good initialization, it seems like we'll always train. Yeah, it has a very clear gradient signal directly to the minima. Dave.
Given the presumably high dimensionality of the network space, how do we get a gradient visual that's so intuitive?
Yeah, so good question. So given the high number of parameters we have, how do we get these visualizations? We just pick 2 random parameters. Yep. So that is a good thing to think about. And oh, we have this too. Okay, we're gonna try to go through this quick. So these are our transpose convolutions. So we've seen ways to shrink the spatial dimensions, but how do we reverse? There are some ideas that people have tried where basically you basically duplicate pixels or do some sort of linear interpolation between pixels. But in deep learning, as always, why not learn how to go the opposite direction? And these are called transpose convolutions. So how does it work? Well, suppose we have an input of size 4 by 4, and we apply a 3 by 3 kernel, convolutional kernel to it to get a 2 by 2 output. I've talked in the past about how convolutions are basically sparsifications of fully connected layers, and this is what I mean. So we can rearrange these convolutions, this convolutional filter, into a fully connected layer with zeros in certain positions corresponding to the positions that our convolutional filter is not looking at in our input. And the result is this. And so we take the dot product of this convolution matrix with our collective input matrix, and it gives us an output of size 4. So we have our inputs, flatten them, multiply them by our convolution matrix, which is just a sparsified, fully connected layer, and it produces an output of size 4. So we can, if we want to go to the reverse direction, we can actually transpose the convolution matrix. And this is the result. We end up with a 16 by 4 transposed convolution matrix with learnable weights in the same locations as we had in our convolution matrix, multiply it by an input vector of size 4, and it produces an output of size 16, which we can then reshape into size 4 by 4. And that is where we will end. Before we go, any quick questions on those transposed convolutions? Yeah.
So how you work with that?
Yes, and so that, yeah, so then the UNet, when we are going and increasing our spatial dimensions, these up convolutions are transposed convolutions. Yep. All right, have a good day.